The standard model has worked fine until now, but physicists realize that it's incomplete. To make the standard model complete, we need to invent something new that will unify the four forces. This is known as the grand unification. In order to do this, we invented something called supersymmetry. Supersymmetry is a principle upon which theories are generated. Supersymmetric theories are ones in which they consider that the matter equations and the force equations to be identical. When this is the case, a theory is said to be supersymmetric. In a supersymmetric theory, you have a cousin particle for each particle in the standard model. The standard model contains hadrons, leptons, baryons, and fermions. What happens in a supersymmetric particle is that all characteristics from the normal standard model particles are kept the same, except the spin. Spin is a characteristic of elementary particles, and it is a measure of their angular momentum. In a fermion, it has half a spin, and in a baryon, it has one spin. And it's classified like this in the standard model. However, in order to solve the problem of the Higgs boson, which is that the Higgs boson is supposedly it's supposed to be very light, but according to the equations, it is very heavy. And to correct that, we invented supersymmetry, so that if a supersymmetric particle, supersymmetric counterpart of the Higgs boson is there, then it has opposite spin, which can cancel out the Higgs field's effect on normal particles, which will make the Higgs boson very light. This interaction will solve this problem that we have. Another problem that we have is that we can't unify Einstein's field equations and gravity to make quantum gravity. In order to make this possible, we first need to solve the problem of gravity. The problem of gravity is known as the hierarchy problem, in which the weak force, which is carried by the W and Z bosons, is 10 to the power 32 times greater than the force of gravity. With this in mind, gravity is very weak, and so we can't use relativity in this, and so we can't unify quantum gravity. Apart from this, supersymmetry has grasped the imagination of many physicists, including Einstein, and he even said that if we solve supersymmetry, it will solve one of the great frontiers of physics. Talking more about the spin difference, if there is no spin difference, then it can mean that the dark matter problem can also be solved. In a TeV scale supersymmetry, we can say that the supersymmetric particles can be the particles which we know to be dark matter. Dark matter is we need dark matter to solve because the galaxy is going much faster than it's supposed to for the gravitational pull that it has. So in order to increase the gravitational pull, we supposedly theorize something known as dark matter. And in order to simplify physics much further, we can generalize the fact that the supersymmetric particles which are the counterparts of the standard model, can be the particles which we know to be dark matter. If this is the case, then we have solved the mystery of mass, the missing mass, which we know to be true in our universe. If we got that out of the way, then other technical motivations include that theoretical problems which have troubled physicists for generations, and the gauge coupling unification, which is similar to that of the unification of the four forces, and the hierarchy problem, which I've already talked about. These are the main motivations of supersymmetry. However, during the CERN operation in Geneva, what we have found is that we have not found any supersymmetric particles. So in order to compensate for this, we have invented something known as spontaneous break symmetry, which is basically when I have told you before that only the spin differs. However, in this new aspect of supersymmetry, what happens is that the mass also changes. The mass negates that of the original particles, and so that can explain why we are not seeing supersymmetric particles because they have no mass. However, you could say that these could be electrons, these could be photons because they are masses as well, but they still carry a unit of energy. What happens here is that we actually don't know. That's why we are still working on supersymmetry, and it's an incomplete process.